an artifact, a fragment from a time long ago. By studying this piece of our past, we better understand our own history. In space, there are also remnants, cosmic fossils, some that remain from almost the beginning of time. These ancient fossils exist as cosmic background radiation, and at NASA, we've developed a unique satellite to probe the cosmic background radiation as a key to unlock the mysteries of the early evolution of the universe. Scientists believe that in the beginning, our universe was very smooth and hot, uniformly filled with matter and radiation. But as the universe expanded and cooled, it evolved until what we see today, 15,000 million years after the Big Bang, is very irregular and lumpy, filled with galaxies and clusters of galaxies. COBE scientist Dr. George Smoot.
How do we go from the Big Bang, this really, when you think about it, very strange situation, the universe being very hot and dense and expanding and filling and turning out full of galaxies and planets and stars and eventually life. You know, how did we get there? How did that happen? Well, something crazy went along to make it happen because our simple models aren't working right now. We're missing a step. It's like a missing link. And we need to find the fossils back there in the early universe, the missing link that'll get us from the uniform universe to the structured universe we have today.
Scientists are looking for the missing link with their studies of the cosmic background radiation. But this radiation has grown extremely cold and faint as the universe has expanded. So cold and faint that Earth's warm blanket of atmosphere obscures it, making it extremely difficult to study from the ground. For our first comprehensive investigation of the cosmic background radiation, NASA's Goddard Space Flight Center, working together with universities and industry, developed the Cosmic Background Explorer, COBE. Getting above our obscuring atmosphere is only the first step. The radiation itself is still difficult to detect. This is because, as it has cooled for billions of years, it's grown fainter and shifted to the long wavelength portion of the electromagnetic spectrum. The radiation is now so cold, it appears in the microwave and infrared regions of the spectrum. Sensitive detectors for these wavelengths have only recently been developed. For COBE, instrument designers pushed this new technology to the limit. The satellite's 3 instruments are extremely precise and very sensitive to infrared and microwave radiation. The instruments also have to be supercooled so that their own heat doesn't overpower the cold radiation they're trying to detect. One cosmic remnant is so cold, it now radiates at only 3 degrees above absolute zero. To keep certain of COBE's instruments even colder, chilled to less than 2 degrees above absolute zero, engineers enclosed them in a very sophisticated thermos bottle. But meeting this challenge raised another. To build systems with moving parts that can operate at such a low temperature for more than a year required very specialized engineering techniques. With development and testing completed, COBE's 3 instruments are integrated into a satellite 19 feet long, weighing 5,000 pounds, that when fully deployed is 29 feet in diameter. The satellite is the culmination of 25 years of work to develop and refine instruments that can detect the remnant radiation from the early universe. COBE scientist Dr. David Wilkinson.
One of the really unique things about COBE is that it's a scientific experiment. From the very beginning, it's like taking the instruments in your laboratory or instruments that we flew on balloons or in rockets years ago and putting those into a satellite package and essentially moving your laboratory into space.
COBE Science Chairman, Dr. Ray Weiss.
COBE is attacking a problem for which it is very hard to get any good observations. In fact, it's dreadfully hard to get good observational cosmological data. And COBE is specially designed so that all the things that might screw up the data or perturb it are, it's put in an orbit which is shielded from the sun very carefully. It's kept cold. And a lot of things have been done so that you don't have to correct so much, and you can trust the data better. So the cosmological information that comes from this, we hope, will be definitive and will be very hard to argue with.
COBE will be launched by a Delta rocket from Vandenberg Air Force Base in California. Once COBE is placed in its orbit, 560 miles above the Earth, the satellite will begin a controlled spin and deploy its thermal shield, solar arrays, and antenna. About a week later, COBE ejects its protective cover to begin its mission, to search for the missing link in cosmic evolution. With COBE, we will study the microwave and infrared cosmic background radiation, two cosmic remnants that may reveal how our once smooth universe evolved into the wondrous variety of the cosmos. The first cosmic remnant shows us the universe about 1 million years after the Big Bang, when primordial light particles were released. The light particles had been trapped because the universe was packed so tightly that the light couldn't move very far without colliding with matter. But as the universe expanded and cooled, particles of matter began to combine, making room for the light particles to travel undisturbed. The light particles released so long ago persist to this day, filling the universe with extremely faint microwave radiation, a cosmic remnant of the Big Bang. COBE project scientist Dr. John Mather.
When we look at the cosmic background radiation, we're actually looking at the dominant form of energy in the whole universe. This radiation fills the whole sky, comes from every direction. And so it adds up to be 100 times as much energy as comes from all the stars, all the galaxies, all the suns, all the planets that people can see with their own eyes. 100 times as much as that. So it's very important to realize we're looking at the dominant energy of the whole universe. This is the remnant of the Big Bang itself that we're studying with the COBE satellite.
One of COBE's instruments will map this cosmic remnant, looking for minute variations in its brightness in different parts of the sky. The instrument has to be sensitive enough to detect variations in brightness as little as 1/1000%. The variations it detects will tell us how uniform the early universe really was. They may show us the very beginnings of a structure that eventually turned into stars and galaxies. Another of COBE's instruments will also study the remnant radiation of the Big Bang to try and prove or disprove our current theory of cosmic evolution. Scientists will use the instrument's measurements to produce a curve showing how much energy the remnant radiates in each color of the microwave and infrared spectrum. COBE's instrument will, for the first time ever, plot this entire curve, and will do it with unprecedented precision. If the curve looks like this, then COBE will reinforce our current theory that the universe expanded and evolved uneventfully, from smooth to irregular. If the instrument detects even minute variations in the curve, it will mean that there were enormously energetic events that took place in the early universe. Events that could explain the filamentary strings of galaxies surrounding the immense empty regions we now see in the universe. Events that would have to be accounted for in our theory. Dr. Wilkinson.
COBE gives us the opportunity to go look in detail at some of the major predictions of the Big Bang theory, and the hope is that those details will either verify or collapse that whole theory.
The second cosmic remnant we'll study using COBE is one no one has ever yet detected. The remnant will show us an event that we think took place about 200 million years after the Big Bang. Primeval gases had collected into individual clouds, which condensed and heated up and developed into the first galaxies. The light from these first galaxies may be visible today as very faint infrared radiation, a cosmic remnant of the 200 million year old universe. This cosmic remnant will be especially difficult to detect because it radiates at the same infrared wavelengths as the dust that pervades our galaxy and solar system. To detect the infrared radiation, One of COBE's instruments is specially designed to separate out the bright foreground radiation. COBE scientist Dr. Michael Hauser.
If we are successful in subtracting out the foreground radiations and definitely identifying a residual cosmic glow, which can be interpreted as the cumulative emission of first generations of stars and galaxies, this is in and of itself a most exciting discovery. This gives us direct evidence of an epoch in cosmic history that has not directly been observed before.
COBE will measure the sky so precisely that it will detect the glow from the first galaxies, even if it is only 1% as bright as the rest of the sky.
What the COBE will tell us at the end of the mission and after our interpretations are done is how we got here, how the galaxies were formed from whatever was there before.
The COBE mission is worth every ounce of effort we've put into it. Cosmology, as you can understand, is a very difficult problem to study objectively. We are given very few fossils on the beach, if you will. Those few that are present and accessible still to us at this time, 15 billion years or so after the primeval chaos, are worth every bit of scrutiny we can give to them.
With COBE, we have a unique opportunity to become cosmic archaeologists, to explore and study fossil remnants of the earliest observable universe, to search for the missing link in cosmic evolution, to push back the frontiers of our knowledge almost to the beginning of time.